Hey everyone. So in this mini series or mini course, what we're going to do is teach a neural network how to play tic-tac-toe, right? And so we all know what tic-tac-toe is. We've played it at some point, in our lives. It's basically XO, right? So for example, let's say I'm saying X and then you play it with a computer. So it says O, you can say, okay, put X somewhere else, and then where would you put the next O, and so on, right? Now, how does we know kind of how to play this game? We know the goal is to try and get the X or the O's to get aligned together, three, either in a row, in a column, or diagonally to win the game, right? But how does a computer know how to play this? But more interestingly, can we teach a neural network, a simple neural network, to play tic tac toe? And that's kind of what we're going to do in this mini series, right? So what we learn is how you can set up a neural network classification problem, or rather convert this simple game into a neural network classification problem. And nothing fancy. We're not going to be doing reinforcement learning or something in this video. We'll get to that at some other point. It's just a simple kind of setting up a neural network classification problem. We've kind of looked at that in the neural networks for classification course series, right? Where we sat and built, a classification problem from scratch, covered each component in a lot of detail. What we'll do here actually is build on that, right? By, however, using a production framework, PyTorch. So we'll implement this with PyTorch. And so you'll see how, we can set up a classification problem with that. And the architecture we're going to be using is a simple multi-layer perceptron, right? So effectively, you can think of the layers as having neurons with activation functions, and they're connected to each other, fully connected. So it's a fully connected neural network, similar to what we have done in the previous series, neural networks for classification, right? And we'll see if this is enough to play tic-tac-toe, right? Now, typically when you're kind of teaching neural networks or building machine learning models to play games, you use more complicated networks. Also, what you could use is reinforcement learning techniques, which actually teach gameplay. But in our case, this should suffice, right? So suppose this neural network now needs to learn how to play. What is the network actually doing? Well, we're giving it the state of the game. So where, basically you can think of it as this board position, where the X's, where the O's are, what are the empty, states. And what we wanted to do is pick where it would place, you know, the the next value. And so we're assuming, let's say in this particular example, that I'm X and the neural network is going to have to place O. And well, does it know, or how does it know to place the O here to block this move, right? So first things first, we've seen that we are giving it state, or rather, it needs to understand the positions. But neural networks, as we know, only understand numbers. So what we need to be able to do is convert those boards before and after into vectors that the neural network can understand. So let's start by looking at how we can do that with the input, right? So what's getting fed into the neural net? What do we need to do for that? So we have this board, tic-tac-toe board. What we're going to do is number each position, right? So we're going to call this 0. Now you could say 1 as well, but as we know, we need to convert it into vectors. And vector indexing, meaning how you kind of call the vector out of memory, starts with 0. So we're going to call this 0, 1, 2, 3, 4, 5, 6, 7, and 8, right? So we've given numbers to each position. And so we have labeled the cells. We can now write this as a table, right? Now what do we need? Well, this is great. We've got the number for each cell. So we've got 8, rows in this table, not including the header. What are the values, right? What we care about is actually not just what the cell is, but what the value in the cell is. So that's the state of the game. So let's say if that cell has X, we're going to say it's 1. If the cell is got an O, we're going to say it's 0, the value is 0. And if there's nothing in the cell, we're going to call it empty. We're going to say the value is -1. So how do we translate this board into numbers? Well, 1, so 0, nothing there, so -1, nothing there, so -1. There's an X there, so 1, nothing at 5, so -1. 6 again is empty, so -1. 7 is -1, and 8 is empty as well. So we have converted this board with XO into now numbers, right? So now you can see the pattern. Now this tic-tac-toe board can be written as a column of numbers: 1, 0, -1, -1, 1, -1, Everything else is -1, right? All the empty ones are -1. And writing that in vector form, we know what a vector is. It's just a column. In this case, it's a column vector. It's just a column of these numbers. So you have these numbers now arranged in vector form. And what have you got? You've got a column vector, which is the state of the game. Now we're going to add one more piece to this vector. What is that? Well, the you what we want the game to understand is where to place the next value. However, the what to place also depends not just on the state here, but also on whose move it is, right? Is X going to play next or O going to play next? So what I've chosen to do here is make that an input state, right? If you've played, then the game knows that it has to play next. If the game has played, then you have to play next, and so on, right? So we're going to give that as an input, to set up our training problem. So what we're going to say is, if X is going to play first, because we'll be training on both X and O data, right? So that the game can play as X or can play as O. So the first player, if basically X, the value will be 1. If the next move is O's, then the value is 0. And if we end up in a position where no move is possible, meaning the board is full, let's say, and we have that state, or the game is over, X is already 1, for example, and so on, then the no move position is -1. What we can do ideally is remove this from the training set completely. But what I've done is give you that value as well. So you can set it up that way and maybe train with invalid states and teach the network to recognize them as invalid states and not play, right? Okay. But what that has done now is added one more value to our input state vector. So what we end up having is, in this case, X, O, X. So the next move is O. So you have the state of the board here, right, which is this state. What you also have is one more value to that vector, which is who's playing next. O is going to play next, so the value is 0. So now a vector state has one more value. So it's the input vector is 10 values, right? It's this state, basically, whether it's X or O at each cell, and who's going to play next, X or O. We're doing this because we're trying to train the neural network. The neural network knows nothing else, right? So we're just trying to explain to it the entire situation with this input vector. Good. So we've got the input to the neural network. What's the next part? The neural network takes care of itself, but now it gives out numbers, right? So how do we what is the problem going to be set up, or what values is the neural network going to give out, right? Which is this board, right? So in this case, it's the move, right? Well, let's start with the state of the board. You have 3 cells where there are values and the others are empty, right? All we need to understand is which cell the neural network needs to place a value in, right? Now you'll be thinking, well, it also needs to know whether to play X or O, right? But we've already taken care of that, right? The input also tells the neural network if the next player, the move it's looking for, is X playing the move or O playing the move. All it needs to figure out is which cell to place the value in. So we're going to give the cells from 0 to 8, right? The input state already tells the network whether it's X or O. All the network has to do is pick the cell. So again, we've already numbered the cells from 0 to 8. And what we'll do in this case, let's say if it has to place an O here, the output will be cell 8, right? But instead of giving it a number, we have a lecture, we've already covered one-hot encoding in neural networks for classification. So you can go check that out. But basically, if the value is 8, you can think of a vector where the 8th entry is 1. If it was going to be the cell here, which is 5, 0, 1, 2, 3, 4, 5, then 5 would be the active cell or the output, in which case you take the 5th value here, 0, 0, 0, 0. This would be 1 and the rest would be 0, right? So that's called a one-hot encoding, where you can take this value and convert it into a vector with zeros everywhere else. And wherever this value shows up, that index is set to 1. So that's the output that the neural network is going to have to match, right? We're going to set it up so that it matches this output, which means it's going to have, in the last layer of the network, it's going to have to give out 9 values. So the last layer will have 9 outputs, and it's going to be trained to ensure that it tries and matches the ideal position that it should take at that point. In this case, something like this. So that's a problem, right? The input state of the board, meaning what the values are and who's going to play next. And the output, which cell does the output, is the output in? which will depend on the state of the board and who's playing, right? So now the question you might have is, what happens to, don't we have to tell the neural network which cells are empty and which are not? No, we're not going to do that. We're going to assume, given the data, that it learns that it should not place an X or an O in a cell that's already occupied, right? The data will tell it not to do that, and we'll see if that is enough to train this neural network, right? Okay. So what's a neural network architecture? We know it has the input vector sized 10, right? Forget about batch mode, meaning multiple batches of data. It's basically, it's got 10 elements to it. So the first layer is going to have, you know, each neuron, basically in this case, is going to have to take in 10 inputs. We're going to have 32 neurons in that layer. So 10 times 32. And then you can keep, so this 32 is optional. You can pick 16, you can make it 64. You can set this. This is an example architecture. And I've explored a few, so I'll probably stick to this one when we implement it. You can explore by reducing the number of neurons and increasing it. So I'm going 10, 32, then 32, 64. So basically 32 inputs per neuron, and there are 64 neurons, so 64 outputs to this layer. I'm going to reduce the size again. So each neuron here has 64 inputs, but now there are 32 neurons. And we know we have 9 outputs, right? It has to give 9 outputs. So the output is 32 times 9. Each neuron gets 32 inputs from this layer, and there's 9 values going on. If you remember a multi-layer, and I'll add links to these videos so you can refresh your memory, but a multi-layer perceptron, fully connected. So every output of every neuron in the previous layer is fed to each neuron in the next layer, right? So that's why 32 outputs. Each neuron here gets each of these outputs, right? And there are 9, so you get the 9 outputs. What kind of layers are these? Well, they've got they're linear, meaning there's sigma WIXI plus B. And then there's also the ReLU activation function. And that's the same for these 3 layers. And the last layer, it just returns the linear output. Right? Now, when you train this, you have a linear output. Ideally, you want probabilities out, so you'd have a softmax, but we don't worry about that because when we train this, we're going to use the loss function, which is the softmax plus cross entropy loss function. So the softmax will convert the output here, which are logits, which are just numbers, into probabilities. The cross entropy then will then compare that with the one hot encoding data, right? So the actual output it should be, and it will try and minimize the loss. And again, we've covered this in quite a bit of detail in the previous videos in the neural networks for classification. So I'd suggest you can go check that out to understand in more detail. But when we implement this in the next video, again, I'll kind of quickly refresh your memory on these topics. Okay, so we need the data for this, right? So what is the data? Well, let's look at an example. In this case, you have an empty board. So the entire set of inputs would be -1. And the move is X. So the next is 1. Right? And in this case, I'm defining this. So this is the ideal output, let's say, that the neural network is going to train on. So I'm saying I want an X to be placed in cell 0. Right? And so in this state, I'm saying the actual output should be an X here. Right? So this. So now if you give this state, what is the data? What is the vector? And what's the actual output we want? That's kind of how the data set is. So again, X is here, so this is 1. All the other cells are empty, so -1. Who's playing next? 0 is playing. O is playing next, right? The second player. So next is set to 0. And then this is the output. Now let's say I want O to be placed in cell 1. So I'm going to tell it that the output should be cell 1. Now, obviously, we'll convert this into a one-hot encoding when it's training. But for now, in this column, we can just represent it as cell 1. What's the next move? So now you have 1 and 0. Everything else is empty, and X plays again. So next is 1. Let's say I'm saying that the next best move here in this situation is for X to play this point, right? So that was 4, right? And so X value is 4. And so for that state, I'm saying 4 should be the answer. So these green values are the actual answer we are giving the neural network. We're telling it, in this situation, you need to, if you were X, you need to put the value in 4. Right? Now, what about here? Well, you know that O needs to play here, otherwise the game's over. So it's 1, 0, -1. So it's empty. And then we have 0, 1, and everything else is -1. So that's that. O is the player. Why do we need O to kind of play? We need it to be placed here. So we're giving that. So it's supervised learning in that we're giving it what we think is the best possible move, and we're hoping the neural network will learn this. What happens here, right? Few more moves have gone. So now in this case, we've got the state. X is the next player. Obviously, to win, we need the answer to be here. So 5 obviously is going to be the data fed to the neural network or the actual truth value, and the neural network is going to train on that. So this is how we're going to set up the data, right? We're going to give it the state and whose move it is, and we're going to pass it what we believe is the best possible move. And then we give it enough data points and we assume that the neural network learns well enough. Now you can think of a few challenges associated with this. You can also think of why reinforcement learning, you know, is actually what is probably used in games more than a simple perceptron, right? And a simple training procedure. But for our case, again, it's an interesting problem to experiment on, right? Okay. So now, how many states do we have, right? So it depends, right? There are so many moves in the tic-tac-toe game. So what we have done is use the minimax algorithm to create a data set, right? So what the minimax algorithm is a machine learning algorithm. And I'm not going to go through that in detail. If you're interested, let me know and I can have a separate video on that. But it's a machine learning kind of a machine learning algorithm that is used actually quite a bit on gameplay. And what it does is given a state and the rules of the game, it's able to iteratively go in. Effectively, you can think of it as playing the game and then kind of coming back and finding the best possible move. So instead of me sitting and playing every variation of tic-tac-toe, what I've done is set up the minimax algorithm and for each given state, use the minimax to find the optimal possible move. So in this case, this is the state using minimax. It comes up with the answer that it's supposed to place O here because what minimax is trying to do is give either player the best chance of winning. So if minimax is playing for X, it's trying to make sure X wins the game, or at least X doesn't lose the game, depending on the state. And if it's playing for O, same thing. It's trying to make sure O either wins or has the best chance of winning in the long run, right? And so I've used Minimax and got different states. So we end up with more than 6,000 data points, right? Or 6,000 board states and the best possible move in that scenario according to Minimax. And then what we're going to do is see if a neural network can learn from this data and actually play the game, right? And so in the next video, what we're going to do is we're now going to implement this. We've seen how to set up the problem, how to set up, convert this game into a vector input and a possible output state. Got a basic neural network architecture, and we've got how we're setting up our data. What I'm going to do next now in the next video is now implement this using PyTorch. So you'll get an understanding of how to quickly set up a problem in PyTorch, which is the idea of this series. But you'd also see how you can how this fun problem can be solved, and then we'll take it and quickly build an app or take a quick Streamlit app for TicTacToe, plug a neural network in and see how it works. Okay, so hopefully you're game for this. See you in the next one.